Well, hello students, welcome back to Mathematics Castles class with me, Mr. Alfie. In this video, we're going to learn about proof in mathematics. But before we learn about it, I'm going to introduce you to some terms. Let's check this video out. First is counterexample. Counterexample is an example that shows the statement is wrong. For example, this is the statement: all prime numbers are odd numbers. We just need one counterexample to prove that this statement is wrong. If we can't find any counterexample for this statement, that means this statement is true. So, all prime numbers are odd numbers. Turns out, 2 is a prime number, but 2 isn't odd number. 2 is an even number. So 2 is a counterexample, the example that shows that this statement is wrong. So this statement is wrong. Next, there is quantifiers. There are two quantifiers. The first is this symbol. This is for all. This is how we use that. For all real numbers x squared is bigger or equal to 0. And then the other one is this symbol. There exists. This is how we use it. For all real numbers x and y, there exists a real numbers between them. And then there is converse. The converse, if P then Q, is if Q then P. You just simply need to remove the order. So example, if x equal to 2, then x squared equal to 4. You remove this statement here and this one to here. So the converse is if x squared equal to 4, then x equal to 2. In converse, if the statement is true, the converse isn't always true. Like this one, the statement is true. If x equal to 2, then x squared equal to 4. But unfortunately, the converse is not true. This is false. Because if x squared equal to 4, then x equal to 2. This is not true because x could be negative 2. And then there is biconditional. The biconditional is the converse of a true statement is also true. So if there's a statement and the converse is also true, it's biconditional. Like this statement: if 2 plus 3 is 5, then 3 plus 2 is 5. Let's see the converse. If 3 plus 2 is 5, then 2 plus 3 is 5. If P then Q or Q then P, then P biconditional Q. So if the statement is true and then the converse is true, so P is biconditional with Q. And then there is contrapositive. The contrapositive of if P then Q is if not Q, then not P. So example, this is the statement: if x equal to 2, then x squared equal to 4. Remember, P then Q, and then it's not Q, then not P. So the contrapositive is, if x squared is not equal to 4, then x is not equal to 2. And then inverse. The inverse, if P then Q, is if not P, then not Q. Example, the statement is if x equal to 2, then x squared equal to 4. So the inverse is if x is not 2, then x squared is not 4. So today we're going to learn about two types of proving in mathematics. The first one is direct proof and the second one is indirect proof.
So in a direct proof, Essentially, we are just going to assume that the antecedent is true and then use the rules of inference, axioms, definitions, etc. to show that the consequent is true. So we're assuming P is true, we're proving Q is true. So that is our goal. We did this a little bit already when we talked about the rules of inference. We did a direct proof, and it was a formal direct proof. So for each and every step, we gave the axiom or rule that we used in order to prove it's true. So on the next couple of examples that we're going to do together, these are going to be direct proofs, but they are going to be informal proofs. Let's do our first direct proof together. So we are to prove if n is an odd integer, then n squared is odd. Now keep in mind, whenever we're dealing with a direct proof, which is what we're doing, we're essentially looking at our propositional logic. We're saying if P then Q, we're assuming P is true. So it's good to think about that when you're starting a proof like this. In this case, I've got an if then, and so it's pretty clear that this is P and this is Q. And therefore, this is an if P then Q. It's an implication. So when I go about proving this, remember I'm going to assume then that P is true. That's a direct proof. Now before I get started on this, I want to talk to you about two definitions that you may or may not be familiar with, but you're going to use them all of the time. When we're dealing with things like even and odd, we need ways to re-express those so that we can manipulate them in proofs or equations. If I'm dealing with an even integer, let's say n is even. If n is even, I can re-express n as 2 times k, where k is some other integer. And of course, the reason I can do that is if you have an even integer, the definition of an even integer is that it can be divided by 2 and the result is another integer with no remainder. If I have an odd integer, say n is odd, n can then be re-expressed as 2k plus 1, because obviously if we take an even integer and we add 1, we get an odd integer. And again, k must be an integer as well. So now that we have everything we need, let's start this proof. When we start a direct proof, we assume P is true. So I'm going to assume n is an odd integer. Based on that, then I'm going to use my definition of an odd integer that says then n equals 2k plus 1, where k is some other integer. And now I'm going to go about proving what I can say by definition. Oops. Got a little extra something in there. By definition of an odd integer. So from there, I'm going to say, where am I trying to get to? I'm trying to say n squared is odd. So if n is 2k plus 1, then I'm going to square each side because I'm trying to get to n squared. So that gives me n squared equals, and then of course I'm going to FOIL this out, so please don't give me 4k squared plus 1 because I can't even. This is 2k plus 1 times 2k plus 1. So FOIL it out. When you do that, you get 4k squared plus 4k plus 1. And that still doesn't help me because what I'm trying to get to is to say that n squared is odd. Now, how am I going to show it's odd? Well, lucky for us, we have a definition of what an odd integer looks like. So I'm going to continue by taking a 2 out of my first two terms, 2k squared plus 2k plus 1. So from here, I'm feeling pretty good because this does seem to be in the correct format. But a lot of people don't like that because there's still kind of a lot going on here. So quite often what you'll see is n squared equals 2r plus 1, where r equals 2k squared plus 2k, and r is an integer. So now what have I done? Now I've said, hey, I've done all of this work. I have found that my n squared gives me an odd integer. So at the end, I'm just going to summarize what I have found. And what I have found is, therefore, n squared is odd. Now, again, those three little dots mean therefore, and a lot of times you'll see then a square at the end of a proof, which is basically saying, hey, I'm done. You might see a little triangle at the end of your proof, or you might see QED. QED is essentially a Latin phrase that says something like what was to be demonstrated, and so essentially we're saying we demonstrated what was to be demonstrated. Here's another proof for us to try, and it's always a good idea to challenge yourself. So if you'd like, go ahead and press pause and try this one on your own. But remember, when I'm doing something with a direct proof, I'm looking at that if P then Q, and this one isn't really written in that format. So if it's helpful to you, not a bad idea to think about what this would look like as an if then. So it says the sum of two even integers is even. So if I add two even integers, then the sum is even. Something to that effect is how I could write this as an if-then statement, which means that I've got two even integers, which is p, and I'm adding them together and getting a sum that's even is q. So for p, I'm basically going to say, I have two even integers. So when I get started on my proof, I'm going to say, assume a and b are even integers, which is essentially what this is saying. Now I didn't include the add, but that's okay because over here sum implies that I'm adding. So assume a and b are even integers. Guess what I'm going to do next? Exactly what I did last time. Then a equals 2k for some k that is an integer, and b equals 2m for some m that is an integer. Now, keep in mind, I have to have different variables for those two. I can't just assume they're the same variable because that would be assuming that a and b are the exact same even integer. So this is allowing for any possibility of two even integers. So that's what I did next. Now from here, I'm going to focus on the math part of it. It says I'm adding the two even integers. So I'm going to take a plus b and say a plus b is the same as 2k, because that's what a was, and 2m, because that's what b was. Now I can rewrite this as 2k plus m, again using the distributive property, and then I can rewrite that as 2r, where r is equal to k plus m, and r is an integer. That was a bad z, but you get the idea. So what I have said is when I'm adding these two even integers, I get some other even integers. So therefore, the sum of two even integers is even. QED. In this method of proof, essentially we are going to assume some proposition is not true, whereas with direct proof we assumed something was true. Through that premise and through logic, we're going to find a contradiction that shows our original premise must have been incorrect and therefore the proposition was in fact true to begin with. So we're going to do this differently depending on what it is we're trying to prove. If we have something that can be written as one proposition, the sky is blue, that's one proposition P. we're going to assume not P is true. So the sky is not blue. And then we would go about finding a contradiction that shows that not P must be false and therefore P is true. If instead we have an implication, an if-then statement, if P then Q, then we're going to assume both P and not Q are true. And then, again, using those same methods, we'll find a contradiction that shows one of two things. So it's either going to show that if P is Q, then Q must be true, or if not Q is true, then not P must be true. So this second one obviously is a proof by contradiction and by contraposition, because this is what we did for contraposition. But let's take a look at how I can prove this now through contradiction. Remember, in a proof by contradiction of an implication, I'm going to assume P and not Q, and then I'm going to work to either show that if P were true, then Q must have been true, or if not Q were true, then P must have been true. So let's get started. I'm going to assume P, which is 3n plus 2 is even for some n that is an integer, and n is not Q says n is even is Q, so not Q is odd. N is odd. So those are my assumptions going in. Again, then you might be thinking, what do I do next? Well, what we do next is we think about what we have and where we're headed. So again, we're trying to show something to do with the parity of P and Q, whether or not P is even or odd, Q is even or odd, etc. So I'm going to start by saying, since 3n plus 2 is even, then 3n is even by subtraction of two even integers. So we know if we have an even integer and an even integer and we subtract them, we get another even integer, or 0, but we're just going to assume even integer. So if I take 3n plus 2 and I subtract 2, then 3n must be even as well. Then 3n minus n must be odd by subtraction of an even and odd integer. However, if we think about what we just said, 3n minus n is equal to 2n, and I just said it's odd, but 3n minus n is 2n, which is even by definition. Which is a contradiction. Of our original assumptions. Oops. Original assumptions. And then, of course, therefore, if n is an integer and 3n plus 2 is even, then n is even.
Prove that if n to the third plus 5 is odd, then n is even. All right, prove this by let's do contradiction first. Okay, prove this by contradiction and contraposition. All right, I just want to show you how to do proofs by using both methods. All right, this is an overkill. In most cases, just using one method will suffice. All right, so let's start with the first method, contradiction. So how do you carry out a proof by contradiction? That's the question. So to carry out the proof by contradiction, all you just have to do is you just have to show, if you have an implied statement as indicated here, you just have to show that the hypothesis implying the negation of the conclusion results in a contradiction. Results in a contradiction. Okay, so if it results in a contradiction, then that means that P implies Q is true. So that's the whole idea behind proof by contradiction. All right, so in this problem, the hypothesis is P. So P is n to the third plus 5 is odd. All right, and then Q is our conclusion, which is n is even. All right, so what we want to do is we want to show that P implies not Q results in a contradiction. So if Q is n is even, that implies that not Q, what is not Q going to be? Not Q is n is not even. All right, n is not even, and that's the same thing as saying n is odd. All right, if a number is not even, then it's odd, so the same thing. So not Q is going to be n is odd. All right, so what we want to do in this proof is we want to show that P implies not Q results in a contradiction, or if n to the third plus 5 is odd, then n is odd results in a contradiction. In a contradiction, okay? So if we can show this, then we're done. Contradiction. All right. So let's start with the left side of our statement. Since n to the third plus 5 is odd, what does that mean? What does it mean for a number to be odd? Since it's odd, let's write it in equation form. That means that n to the third plus 5 is equal to 2k plus 1 for some integer k. And this is by definition, okay, by definition of odd. All right, so we have this situation here. Now let's try and isolate. Let's see what n is, okay, using this equation. So we're just going to subtract 5 from both sides and take and then see what we can determine from there. So if we subtract 5 from both sides, we have n to the third plus 5. I'm sorry, n to the third. If you subtract 5 from both sides, that's going to be equal to 2k plus 1 minus 5. N to the third is going to be equal to 2k minus 4. Let's see on the right side. What can we do on the right side? Notice we can factor out 2 equals 2 times k minus 2. And k minus 2 is an integer because we know that integers are closed under addition and subtraction. Okay, so k minus 2 is an integer by closure. So let k let's k minus 2 equals, let's give it letter m, equals m for some integer m. All right, so what do we have now? We have n to the third is equal to 2m. All right, now let's go ahead and decompose this exponential expression right here. N times n equals 2m. Now, since 2 divides the right side of this equation, what do you think about the left side? Since they're equal, 2 has to divide the left side of the equation also. Okay, it has to divide at least one of these factors, all right? So since 2 divides m, then 2 divides n, the first number, the first factor, or 2 divides the second factor, or 2 divides the third factor. All right? Because 2 divides the expression on the right. So which of these does 2 divide? Well, they're all the same, right? So since n is equal to n is equal to n, that implies that 2 must divide n, since they're all identical. All right? So if 2 divides n, then n is even by definition. Okay, because 2 divides every even number. All right, so but what was the conclusion of the statement that we started with earlier? We said that if n to the third is odd, then n is odd. But we started with n to the third plus 5 being odd, and what did we end up with? We ended up with n being even. All right, so this is a contradiction to the conclusion that n is odd. All right, so this basically completes the proof that if n to the third is odd, then n is even. All right, so therefore, if n to the third plus 5 is odd, then q is true. Okay, then n is even.